All right, so I made a couple mistakes here. Actually just one mistake, but I forgot to square root this value. So I got 0.123 and that was wrong. The corrected value is 0.35 when you take the square root. And so that's what I have, that's going to be my actual value here in this phasor for VX1. I went ahead and did the same math for VX2 and got VX2, but I don't want to take too much time doing the exact same thing that I already did. So if you want to practice, go ahead and you can utilize this as an example. But this is what I got for VX2. And so now what I need to do to finish this problem is I need to add VX1 and VX2 so that I can get my final value for VX. And if you notice, VX1 and VX2 are almost the exact same, but let's go ahead and do the math anyways. So on this last page, let me just copy my value for VX1. Sorry, it's going to include the red. We can correct it. But let's just bring that here. And then we'll come here and grab this one as well. All right, I guess I used two different pens. That's why the thickness is not the same. And then we'll grab our final circuit just so that we have it. Throw that up here again. And let's just go ahead and do this math. So again, addition for complex numbers is much easier when we're not in the phasor domain. So let's go ahead and convert these back out of the phasor domain. We know that r cosine of theta, or phi in this case, is equal to our x value, and r sine of phi is going to be our y value, where these two create our x plus jy complex number, right? So for Vx1, we can rewrite that as basically going to be r, so it's going to be 0.35 times the cosine of negative 61.97 degrees, plus j times 0.35 times the sine of negative 61.97 degrees. And that's going to be, let's go ahead and compute that. Let's make sure my calculator is in degrees. It is. So I get cosine of negative 61.97 gives me a value. I multiply that by 0.35. I get 0.164 plus j times some value over here that we're going to get. So let's do sine of negative 61.97. Multiply that by 0.35. It actually comes out to a negative value, so let's change this over to a minus j times 0.309. All right, that's going to be our Vx1. For Vx2, it's very similar. We're going to do 0.35 times the cosine of negative 61.89 plus j times 0.35 sine of negative 61.89. Correct my 0 here. Let's go ahead and do that math. Vx2. And let's also actually just move all this over so that I have more space. So Vx2 is going to give me, so let's do cosine of negative 61.89 times 0.35. I get 0.165. And then I'm going to get another minus. Let's do sine negative 61.89, and that's multiplied by 0.35. Okay, so I get another minus j 0.309. And then I have to add these two values together. So I'm going to get Vx, my final value for Vx is going to be Vx1 plus Vx2, which is going to be equal to, so I can basically add the real parts, 0.164 plus 0.165 plus j, or I guess I can just do minus j, times 0.309 plus 0.309. All right, and that's going to give me, let's just do it. I don't feel like doing the mental math. 0.329 minus J 0.618. That's my value for Vx. And I can convert this into a phasor by R is equal to the square root of 0.329 squared plus 0.618 squared. 0.329, 0.618, and then I have to add those. Take my square root, I get that R is equal to 0.7, and then my angle is going to be the tan inverse of negative 0.618 divided by 0.329, negative 61.97. All right, so my final value for Vx in phasor is 0.7 angle negative 61.97 degrees volts. All right, if I wanted to write this in the time domain, should be fairly straightforward at this point. I'm just going to write Vx of t is going to be equal to 0.7 times the sine of omega t, where my omega in this case would have been 2 pi times 1 megahertz, right? Minus 61.97 degrees volts. And that is the end of the superposition problem. Hopefully that works. Yeah, no. I should have never tried to go and get the omega value in there. Just box this and then cut off the arrow. All right, that is, oh my gosh, the box isn't even straight. There we go. That's the end of this problem. Again, you can just see that the math is pretty tedious. It does become pretty repetitive pretty fast, but this is all chapter 10, sinusoidal steady state, just kind of covering our bases here. Want to make sure that all of this math makes sense and that we can solve these problems by converting between rectangular and polar coordinates. And if you have any questions, please feel free to let me know, but I'm going to go ahead and wrap this up. And then in the next couple of videos, we'll be looking at mesh analysis, and then we'll look at Thevenin and Norton, and then we'll look at some op-amp circuits, and then we'll be done with this chapter. So I'm going to go ahead and end this video right here.